Hi everybody, this video is going to be about titration problems. This is the last part of chapter 17. So we kind of need to talk a little bit about what a titration is to begin with. So when you think about a titration, you're mixing an acid and a base. One has known concentration, the other one has unknown concentration. You might also get problems associated with what's the pH in this situation. That's not really the point of a titration. A couple of terms. Equivalence. Equivalence is the point at which moles acid and base added are equal. So if we start off with acid and we add base to it, then the moles of the acid we started with are equal to the moles of base that we added to it. So the addition, those things are equal. Pre-equivalence is any point before the equivalence point. Post-equivalence is any point after the equivalence point. The endpoint is one other term, and this is when your indicator changes color, which a lot of times you're hoping is going to be equal to or close to your equivalence point. Unless you're not trying to find equivalence point, then you might have it change color to a different point. Types of titrations. So if you have a strong acid and a strong base, this is really pretty easy because strong things fully dissociate, so this is just a stoichiometry problem. It doesn't matter if you're at, before, or after equivalence. This is really just stoichiometry. To figure out how much of everything is there. Weak acid, strong base. If you're after equivalence, if you're after equivalence, you're doing stoichiometry, but if you're before equivalence or at equivalence, then this is more of an equilibrium problem. Realize that if it's a weak acid, strong base, that means the strong base is going to fully dissociate and react. That means it's going to turn the weak acid into its conjugate. Its conjugate is also a weak base. So at equivalence, when there's no strong base and no weak acid around, all you have is weak conjugate base, which makes it basic at equivalence. It's acidic before equivalence because it's a weak acid. Obviously, there's a little region in there before equivalence where it might be basic depending on its K value, but let's not worry about that. And it's basic post-equivalence because you are adding strong base in. If you have a weak base and a strong acid, these are the same. This is basically the same except flipped in that it's going to be basic before equivalence. As you continue to add your strong acid, it's going to react until finally at equivalence it's going to be acidic, and then post-equivalence it's going to continue to be acidic. You're not going to see weak base, weak acid titrations because these don't really accomplish any goal because there's too much equilibrium happening. You need at least something to go to completion in order for you to do stoichiometry. And so the weak acid, weak base situation, it's too confusing and doesn't accomplish the point. Alright, so let's solve a couple of problems. So, can't figure out where to put myself here. Alright. Calculating unknown concentration and equivalence. This is basic stoich that we've done before. Think chapter 4. So, if you're calculating a concentration of something at equivalence, all you're going to be saying is, okay, what's the reaction? Writing it out. You're looking for how many hydrogens, how many hydroxides, so you know the mole ratio. If the mole ratio is 1 to 1, as it is in this problem, then what you're going to be doing is you're saying, okay, how many moles do I have? So 0.2 liters times 0.1 moles per liter times my mole ratio. That gives me my moles of acid. And then I divide that by my initial volume of acid. Now, it's the initial volume of acid, not the total, because I want to know what the initial concentration is. If I want to know the equilibrium concentrations, then that's going to be a different problem altogether. Okay, so if I want to just know the initial concentration, and that's given, we're taking it to equivalence, and I'm saying, now that I'm at equivalence, I know something. I know how many moles of acid I had. So now I can come back and say, hey, what was the initial concentration? And that's what you're solving for. And that's what most titrations are solving for. Now that's pretty easy. So let's make it harder. And so it's going to be harder by not trying to know what the pH is at every point. When you have strong titrations, again, this is just a stoichiometry problem. At equivalence, it's normal stoichiometry, and pre- and post-equivalence is normal stoichiometry. Pre- and post-equivalence, the only difference is that you're dealing with a limiting reactant. Your titration curve looks like this, where there's very little change up until you get right around equivalence, and then there's a large dramatic change. It's pretty much what all titration curves look like. If you don't understand why that is, it's mainly just because of the fact that this is a logarithmic, pH is a logarithmic scale, and the relationship between OH and concentration of H plus is an exponential scale. And so you're going to get this big, tall curve here. Anyway, So if we have an example problem, 100 milliliters of 0.1 molar sodium hydroxide added to 200 milliliters of 0.1 molar nitric acid, what's the pH? So figure out how many moles of each you have. So 0.01 moles of hydroxide, 0.02 moles of hydrogen ion. Because they're both strong, they both fully dissociate, so all I need to do is stoichiometry. I'm going to subtract the two of these, and I end up with 0.010 moles of hydrogen ion left, and divide that by the total volume. So I want to know the pH of the whole thing. So there's 300 total milliliters, and so that gives me 0.033 molar H+, which gives me a pH of 1.48. Now, if you have a strong acid, weak base, or vice versa kind of titration, these problems they need a little bit more work to deal with them. You can kind of break them down into different phases. You can talk about what happens before the experiment, which you just solve like a weak acid problem. You can talk about what happens before equivalence, which is going to be your weak acid and weak conjugate base both being present. This is going to be like a lot of the buffer problems that we've done so far. And you can figure out at equivalence. This is just a weak base problem. This is just like what we did in chapter 16. And we can do post-equivalence, which is really a stoich problem like we've done before. So the biggest difference here is in the before equivalence point, and that's just like a buffer problem. So I'll go through and show you how to solve all these, but first, just to look at these titration curves, if you have a weak base and a strong acid, you're going to start off with your weak base. It's going to be a basic pH. As you add acid, you get your same titration curve. This would be the buffering region in here, somewhere in this area right here, plus or minus a pH unit when you come to the pKa value. pKa value is right here because it's just halfway to equivalence, so 25. So then this would be 12.5, come to 12.5, come up. So that's your pKa. Anyway, and here's your weak acid, strong base. You start off acidic. Again, you can see this would be pKb. This would be your pKa right here, and it's an acidic because you're starting off with weak acid. Your equivalence is above 7 because you have weak conjugate base present. All right. So all the different phases of your titration curve. If you just start off, so this is beginning the experimentation. If you have 100 milliliters of 0.1 molar propanoic acid, which we'll call HPRO, and the Ka is 1.32 times 10 to the negative fifth, what is the initial pH? So just set up a normal K expression, x times x over 0.1 minus x, ignore the 0.1 or the minus x, you get x is equal to 1.1 times 10 to the negative third, and then the pH is 2.94. So acidic, you're starting off with weak acid, that all makes sense. If I go to the next phase, which is before equivalence point. So if I have 100 milliliters of 0.1 molar propanoic acid, and I add 30 mils of 0.1 molar sodium hydroxide. So the first thing you want to do is do some stoichiometry to solve for moles. So 0.1 liters times 0.1 moles gives you 0.01 moles of propanoic acid. 0.03 liters times 0.1 molar gives me 0.003 moles of hydroxide. Because the hydroxide is going to react to completion with the propanoic acid, just subtract that. And so you end up with 0.007 moles of propanoic acid left over. Realize that because this 0.003 moles that reacted, it reacted and turned into propanoate ion. So this moles base added is the same thing as the propanoate ion formed. Now I need to work with concentrations, not moles, so I'm going to divide by the total volume, which is 130 milliliters. So I get 5.4 times 10 to the negative 2 molar propanoic acid, and I get 2.3 times 10 to the negative 2 molar propanoate ion. Now that I have propanoate ion and propanoic acid, I can just come back to the Ka expression. Propanoate ion concentration times H plus over propanoic acid. My H plus is 3 times 10 to the negative fifth molar, and my pH is 4.5. All right, what happens if we're at equivalence? So if I have 100 milliliters of 0.1 molar propanoic acid and the Ka, what is the pH at equivalence? So if you look at propanoic acid has one acidic proton. Sodium hydroxide has one hydroxide to donate. So they're at a 1-to-1 molar ratio. So that means that I would have to add 100 milliliters of 0.1 molar sodium hydroxide to get to equivalence. If you didn't see how I got that, go back to the original slide and you can do some math on that. This basically means that you got 0.01 moles of propanoate ion, and you're going to have 200 in the 200 milliliters. There's really not much of any propanoic acid because it's fully reactive. And there's no excess hydroxide because that has fully reacted. So there's no excess hydroxide, there's no excess propanoic acid. The only thing that's acting to change the pH is your propanoate ion. So if you figure out the concentration, it's 0.050 molar propanoid ion, and you're just going to set up a Kb for this. So Kb is Kw divided by Ka, which is 7.6 times 10 to the negative 10th. And so then this is going to be x and x over 0.05 minus x. So when you solve this out, you get a pOH, because that's what x is equal to, or x is equal to OH concentration. Take the negative log, you get pH of 8.79. Now again, we have a basic pH, which makes sense because the only thing acting here is weak conjugate base. All right. Finally, what happens when you're past your equivalence point? So here, if I have 100 milliliters of propanoic acid, and then I add 300 milliliters of 0.1 molar sodium hydroxide, what's the pH? So, just like we've done before, we're going to solve for number of moles of each. So 0.01 moles propanoic acid, we solved for that before, 0.03 moles of sodium hydroxide. We're going to subtract for the moles that react. So 0.03 moles sodium hydroxide minus 0.01 moles of propanoic acid that react mean that I'm going to have 0.03 moles of sodium hydroxide left over. You can ignore the 0.01 moles of propanoate ion that are created because it's really not going to have an effect. Unless you're extremely close to equivalence, you can ignore that. And how would you know if you're extremely close to equivalence? Well, when you solve for this, if your moles of acid and base are very similar, then you're going to be very close to equivalence, and so you might not have to ignore that. And that's going to create a much more difficult problem. We're not going to go into that. So we've got 0.02 moles of sodium hydroxide left over. That is in 0.4 liters, which is the total volume of everything, which gives you 0.05 molar hydroxide ions, which gives you a pH of 12.70. So very basic, which would make sense if you're very far past equivalence. Okay, so that's pretty much everything about titrations. Make sure that you guys know how to solve these problems. You are guaranteed to see problems like this on your test, and you're pretty much guaranteed to see problems like this on the AP exam as well. Good luck, and please ask questions in class if you have any questions. All right, take care.